Hey folks, we're going to take a quick look here at an asteroid that was just discovered. This is 2012 KP24. There are only 14 observations at the moment. Most of those come from the Mount Lemmon survey that discovered it. A couple come from an amateur in Great Britain, and I put those together and ran observational Monte Carlo on it. Just generated 1,000 points for the asteroid just to see whether it's a threat for impact here. First thing to note is the thick white line at aphelion. Basically, that means that we don't know very well where it's going to be in the future. So if you've been on the JPL site and you've seen the condition code, last I checked it was 8. Started off at 9. That's how asteroids start off, and we only have a few observations of them. And basically that condition code is to let us know that it needs more observations, or else we're going to lose it for future passes, because depending on how far it gets from the sun, it will drastically alter where it will be in the future. So right now we know pretty well where it's going to be, but when it gets farthest from the sun, it could have an aphelion that's a little closer, a little farther away. And if it's closer, it's going to travel faster. If it's farther away, it's going to travel slower and take a longer circuit around the sun. So if you extrapolated this out a few years, you'd have no idea where it would be along the orbit by that time, and you'd have no way of finding it again. So that's why we have the condition code. Basically, it's a warning flag that says, hey, we need more observations if we want to find this object again in the future, not, hey, it could hit Earth. So we're going to take a look at what it looks like when you zoom in on Earth and see just how much certainty we have that it will or won't hit Earth. So in this case, the uncertainty is not in a flat direction relative to the ecliptic. It's got a vertical component to it. But if you fast forward through time, we're starting here on May 28th at midnight, and that's the date of closest approach. You fast forward. Oh, I can't see the Earth. Well, let's go around here on this side. And there's the Earth, missed by all the asteroids. Now, this is a real quick test, so don't have the 37,000 asteroids that I had during the last test I did on 2011 AG5. But we really don't need that to just get an idea of whether an impact is even a possibility at all or not, because one of the keys to look for is not only are the blue dots hitting it, each blue dot representing one potential position of the asteroid in time, and not only what's the concentration of the blue dot, so it's most likely to be here in the center, less likely to be further away, but is the Earth between any of the blue dots? If it ends up between a pair of blue dots, then there's a chance that if you continued sampling to a greater extent and added more and more and more potential positions of the asteroid by allowing the Monte Carlo to continue, at some point you would get an impact. So that would at least tell you, no, you're not seeing impacts here, but you could see impacts if you sampled it more. But none of this is the case here. It misses the Earth completely, and the Earth does not end up between any of the possible positions of the asteroid. It's a clean miss. It does get close, and as you can see, the moon's way out here at the edge of the screen. The asteroids are much closer to the Earth, and indeed NASA projects the miss distance to be about 1/10 of the Earth-Moon distance. Looks about right here, just eyeballing it. But it is a clean miss. We don't know exactly what the time of closest approach is. There's about a 45-minute uncertainty there according to NASA, and that's why this line is a long train, because depending on where it is in that line, the miss will be sooner or later. But it will be a miss in any case, and it is not a threat for impact, even though the uncertainty code is currently an 8. Again, that uncertainty code means if you zoom out, and you zoom out, you zoom out, you zoom out, and you take a look at the overall orbit, we have a problem here in terms of trying to project where it's going to be in the future. It gets quite large, quite wide, and so we need more observations to be able to nail down the orbit, which I'm sure we'll get, and be able to say with certainty where it's going to be in this line, and therefore where it's going to be in the future. When is it going to come back close to the Earth's orbit again? So we need that for predicting future close approaches, not this close approach. But that, again, is why we have the uncertainty code, because it is very important that we get more observations. We don't want to lose this object we just discovered and have trouble reacquiring it later on. So that's why that number exists. It's basically a number for astronomers. It's to let us prioritize what needs to be observed, and this definitely needs to be observed so that we can better determine the orbit, but not because it's a threat for impact right now, because it's not. So there you have it. Have a nice day.